The Books Podcast, presented by Tim Hague.
In 1899, Max Planck solved an abstruse physics mystery known as the ultraviolet catastrophe by proposing that energy comes in quanta, little parcels. And the revolution which followed in the next quarter century exploded the classical model of reality, which had served Newton and his kind so very well. And it introduced an entirely mind-blowing new paradigm based on uncertainty, probability, and subatomic realm of existence, which sometimes seemed to be composed not of stuff, but of mathematical equations. Well, I say a quarter of a century, but of course that's nonsense, isn't it? The revolutions continue to this day, and it's the premise of Paul Davies' new book that not only have we not reached the end of the process, but we're embarking on a second revolution, which he calls Quantum 2.0.
This is the shut up and calculate stall. That's a very perceptive question because it goes right to the heart of the whole debate about how we to make sense of the quantum world. If there is intelligence at the quantum level, that would be truly, truly alien. It would have godlike capabilities. The helmet that can peer inside your head and read your thoughts.
I ask you, gentlemen of the jury, is this the kind of book you'd like your wives and servants to read?
Paul, thank you for joining us on Books Podcast.
My pleasure.
Now, you rather sweetly promised that the reader won't need to do any maths, and you are as good as your word, so that might make me your ideal reader, actually. So thank you very much for that. But you do start out by pointing at an equation, which is Schrödinger's 1926 game changer. I want to ask, what is that equation? What does it do? And why is it your jumping off point?
Well, part of the reason is that we're almost exactly 100 years from when Schrödinger's paper appeared. Now, Erwin Schrödinger was one of the founders of this subject we call quantum mechanics. You mentioned already that the term quantum had been coined by Max Planck a quarter of a century before, but nobody really understood what was going on. And Schrödinger and Heisenberg in 1925 were able to basically flesh out the idea into a proper theory which had predictive ability. And this equation, Schrödinger's wave equation, was published on the 27th of January 1926. So we're almost exactly 100 years as we sit here and speak in Broadcasting House. So that was the start, really, of this subject called quantum mechanics, which then grew and grew and became the enabling science behind much of modern technology.
And what that equation, you say, what does it describe? Because presumably it references something that that we would recognise or might not.
Well, it's often called a wave equation, and I should say, even if people have not heard of Schrödinger, they've probably heard of his cat.
Yes, of course.
We'll come back to that. But it describes a wave equation because the big issue in the early 1920s was what is matter? So atoms and electrons, particles, what are they? Do they always behave like particles? And it was discovered in experiments in the early 1920s that they really sometimes behave like waves. And this was the flip side of the fact that when Planck and then Einstein introduced the notion of light coming in little lumps, we now call them photons, that light could be like waves or it could be like particles. And it turns out that matter can also be like waves or particles. So what were these matter waves? And Schrödinger's equation described how those matter waves change and slosh around and move through space and time. But what were they? At the time he wrote the equation down, nobody quite knew how to interpret it.
So how did he know what the equation should be?
Well, physicists know how to write down a wave equation. This is very elementary stuff.
Because, of course, we're familiar with waves within matter.
That's right.
So it's a wave equation then applied to something else.
And nobody quite knew at that stage what. And now, well, very soon after Schrödinger wrote the equation down, Max Born came up with the idea that these are waves of probability. They're not waves of stuff. Now, this sounds a bit abstruse, but I can give you an analogy. Police will often say, well, there's a crime wave spreading through London. So what does that mean? Is there some criminality stuff moving around across the city? No, what we mean is it's a higher probability, higher chance that a crime will be committed where the wave is most intense. And the same thing with these probability waves. What you mean is where the wave is biggest, that's most likely where you will find the particle if you look. So it's both wave and particle. The wave describes how likely it is you're going to find something, and the particle is what you find when you look.
Well, you talk quite a lot about the sheer weirdness of quantum theory in the book, and you come back to it several times. Oh, and you've got a lovely quote from the evolutionary biologist JBS Haldane, that not only is reality strange, queerer, he says, than we imagine, but it's queerer than we can imagine. And he's sort of right. I've got a quote from the book. It's a question, so I'm going to put it back to you. Is this magical metaverse really merely an abstraction, a mathematical frolic of interest only to physics and philosophers, or does it in some sense really exist? Now, I find that a really interesting question, and it's one that your book circles around endlessly. Does it exist? What is real?
Yes, well, this is all about the nature of reality. So there is no doubt in most people's minds that the everyday world is really out there. There's one world, and we've got tables and chairs and things, and we think there's one world and it exists whether we observe it or not. But now, if you drill down to like atomic dimensions, the reality dissolves away into sort of ghostly amalgam of contending alternative realities. I call it reality soup. It's like a blend of all different possible situations. So, for example, if we're talking about the position of an atom, according to quantum mechanics, an atom can be in many places at once. What does that mean? What it means is that there are many contending places it might be in, many contending realities, but they're all melded together in this wave-like form. Now, when you do an actual measurement, when you think, well, let's find out where is the atom, and you look to see, and you find it to be somewhere, that projects out from this array or multiplicity of potential realities a particular real deal. The electron is at, or atom is at a particular place. And that seems deeply mysterious. I'm getting to your question about how do we think of this? Are these all equally real? These different positions, and physicists can't quite make up their minds as to how to think about this, whether, as I've described it, these are just potential realities from which you project just one particular reality with a certain probability, or are they somehow like parallel realities, real worlds coexisting all around us? And there are alternative schools of thought. But whatever is the case, and this is really important to understand, that it sounds like we're just talking science fiction here, but this reality soup, engineers are busy exploiting it. They can manipulate that soup and create states of affairs that can be monetized. So this can be the basis of technology, and indeed the whole quantum 2.0 that refers to the emerging technologies that come out of manipulating this reality. It's reality engineering down at the atomic level. So to the extent that you can make money from devices that exploit this really weird state of affairs, shows that there's something to it. I always got to be careful with the word reality, because it's a loaded term, but there is something to it. You have to take it seriously, because you could make a lot of money and develop a lot of technology. We have quantum computing, quantum sensing, quantum cryptography, quantum teleportation. All of these things are real devices, and they come from manipulating this reality ambiguity down at the atomic level.
But there's an argument, isn't there, that goes back way back to the beginning of quantum theory, which is whether you're looking at something that is real, or whether you just say, well, it works. I mean, you've got another quote about saying it just works, and we can do all this quantum engineering without really knowing whether it's true or not.
Yes. This is the shut up and calculate.
Shut up, yes.
And the vast number of quantum physicists belong to that. They don't worry themselves about what does it actually mean. They just think, well, we have this theory given to us by Schrödinger, Heisenberg, and others, and then we can write down the equations, we can predict what is going to happen, we do experiments and test it. It works beautifully. It explains everything that you could so far investigated, the nature of matter, all the way from subatomic particles up to stars. Brilliantly successful. All this technology, the laser, the superconductor, the transistor, high definition TV screens, MRI machines, nuclear power, it all flows from this wonderful thing called quantum mechanics.
And to be clear, would we have had those technological developments without quantum theory? Would somebody have come up with GPS if it had not been for Schrödinger and Born and Niels Bohr and that crowd laying down the markers?
Well, I don't think so. There's always this problem about scientific progress. We can look back through history and ask, how much was inevitable and how much was a product of brilliant minds and so on. Through trial and error, you can sometimes find how to do things. But to me, it's inconceivable that the whole gamut of the modern world, all of electronics and communication technology and the things we take for granted would have been the product of just lots of little trial and errors. In principle, it could happen. It might take a million years to come up with a mobile phone, just from combining all those little quantum effects together. But really, I think this is the way theoretical physics works. You get clever people who think abstractly and they apply mathematics and they come up with a novel idea, a new way of thinking about the world, and make predictions from it. And these predictions get tested. And time and again, electromagnetic waves, gravitational waves, antimatter, nuclear power, all these things were conceived theoretically before they were actually implemented.
Another thing that I'm absolutely dying to know, and it's one of the happy things about having a proper physicist sitting opposite, is there's all these terms that we keep using about subatomic particles, about the quantum realm, things like energy, momentum, position, rotation, spin. I don't know if spin is different from rotation, but I want to know, are these words placeholders for properties we just can't visualize? Or are we actually saying that quantum objects are rotating, presumably relative to something else? Or are we just finding familiar terms for something that we that's weirder?
That's a very perceptive question because it goes right to the heart of the whole debate about how are we to make sense of the quantum world. And historically, what happened was, well, first of all, physicists came to understand the everyday world. We call that the classical world, how objects move, and we have concepts like spin and energy and movements, speed. All of these things were sort of well established. And then obviously physicists wanted to apply those to the atomic and subatomic world. How fast is an electron moving, for example, and how much energy does it have, and on all of these things. But these are classical concepts which are being imported into this wonderland of blended alternate realities. And there are a lot of physicists who think we've got this upside down or back to front, that the world is actually quantum mechanical, and these everyday terms like energy and spin and speed and these things should emerge out of the quantum world, and that in a future quantum mechanics, you would simply take the quantum properties as the primitive ones and then derive the classical world from it. There are two schools of thought. Niels Bohr, who was like the godfather of quantum mechanics in the 1930s, insisted that the theory only made sense when we accept the existence of a classical world. And I'll give you an example. You can say, did the atom decay? And I can say, yes, I heard the click in the Geiger counter. And that's a statement that I can make to you in terms of everyday concepts.
And he was very firm about that. It only counted if you could. He called it the reality onus.
Yes,
didn't he?
Yes, and it had to be communicated in plain language so that you could say this has definitely happened, that this has brought to a conclusion, the atom has decayed. Whereas quantum mechanically, it's much more sort of wishy-washy, and it just raises the question about whether there will ever be observers that are themselves quantum mechanical that would not use this classical language, quantum intelligence.
But you say in the book that if there ever is like a quantum device, a quantum sensor that can detect what's going on there, it might communicate it to us and we wouldn't understand it.
That's the problem. So we're used to AI. When we talk about AI, people are now in thrall of AI and they worry about it and debate whether or not AI is conscious. Is AI an agent and so on. We don't need to get into that. The point is that whatever your conclusions about that, AI might be amazing, but we understand it. It's like a superhuman in the sense that it's doing the type of things that we do, but better, faster. But a quantum AI, QAI or quintelligence as I call it, quantum AI would be truly alien. Truly alien, because this would be a mind, if you like, that would exist in this reality soup, this multiplicity of realities. It could, in theory, explore all of those potential alternative
Are we going to have to mention
realities.
Hilbert's space?
Well, we could do if we're allowed to.
Yeah, we are. Oh, yes, yes, we are.
David Hilbert was a very famous German mathematician, very distinguished about the turn of the 20th century. And a particular mathematical description which you need for quantum mechanics is called a Hilbert space. It's an infinite dimensional space generally. And the way we think about how a quantum state evolves, let me first contrast it with everyday life. How does a little ball, for example, move around in three-dimensional space? It has a trajectory. We can understand that. But now we've got an infinite dimensional space, and the quantum state might be like a little ball or a little spot in that infinite dimensional space, and it will move around as well. But it's got an infinite number of dimensions to move in. And that's the general description of what is happening at the quantum level. Mathematically, it is a point or it's actually like an arrow in this infinite dimensional space. And that's the way you describe it mathematically. Now, if that was more than just a mathematical metaphor or procedure, if there is something like intelligence at the quantum level, it would be free to explore this infinite dimensional Hilbert space, as it's known. That would be truly, truly alien. It would have godlike capabilities. And the question is then, could we make any sense of it? Could it make any sense of us? Because we're like a very,
could we be in any trouble?
Well, of course, this could be yet another type of apocalypse. But I think the point is that I can imagine that we might create such a thing and then ask it what it thought of us and our intellectual capabilities. And it would obviously have a very dim view because we can see only one world, and we can do these experiments. We might measure the position of an atom or something, and we just project out one reality, whereas this intelligence would see all of the infinite number of possibilities, so they see them all at once. So I have no idea what it would feel like to be a QAI, a quantum artificial intelligence, a quantum mind, a quantum supermind. But such a thing, if you believe that mind is not something which is sort of added on to matter, if mind is something that emerges out of complex matter, then I see no reason in principle why a QAI, a quantum intelligence, could not be made. And that, as I say, we will then unleash something which is truly alien and in some sense godlike. That's an awesome thought. I might say this is like the extreme end of the speculation in my book.
Yeah.
But I think people are pretty fascinated at this time by AI. And so we have two revolutions taking place. We've got the AI revolution, which is, as I've explained, it's not alien intelligence, it's just very good human-like intelligence. Then we've got this whole quantum computing revolution taking place. And people certainly talk about quantum artificial intelligence. It falls short of what I just described, a conscious quantum computer. But there's no reason I can see that we couldn't have such a thing maybe within 50 years.
If there's anything anybody knows about quantum mechanics, it's that it's measurement that collapses the wave function. And you've talked about how we've got waves of probability, and then you measure a particle or something, and then you know where it is, or you know what its momentum is, because of course Heisenberg said it's uncertain. You can't have both. But I think that leads some people to think that perhaps what we think of as reality is dependent on at least a measurement, or in principle an observer, and that's always worried me, because it suggests that if before there were people observing these things, that nothing was real. But then you also reference something called relational quantum mechanics,
Right.
which I found slightly comforting. And I read Carlo Rovelli's book, Reality is Not What It Seems. And he's a strong advocate of that as well. Briefly, tell me what that is, and tell me whether you think he's flaky, whether you believe him.
Right. So it's certainly not flaky, but it's one of about a dozen contending interpretations of quantum mechanics. So let's go back to basics. So what quantum mechanics begins, the big puzzle is that isn't a single reality at the atomic level as there is in daily life. And what are we to make of these contending possible realities? And we've talked about you do a measurement or an observation and you see one thing. And again, the standard quantum mechanics, which is due to Niels Bohr, says that when you do the measurement, you don't just uncover a pre-existing reality, you bring it into being. So if I decide I'm going to measure the position of an atom, I bring into being an atom at a place. And it's not a matter of, well, where was it before? Was it there all along, or was it somewhere else? There's no fact of the matter.
Did it just not have any properties in the sense that?
Well, you bring into being an atom with a position from a prior state of positionlessness. It's not a different position or one that we don't know because we're too clumsy.
And it's not something that was just there unobserved.
No.
The act of observation is what?
The act of observation promotes this, potential reality into an actual reality. It's a creative act. But the weird thing is I can choose to measure something else instead. I might measure its speed, and then I bring into existence an atom with a speed. But an atom with a speed is not the same as an atom at a place. So my decision of what to measure affects the nature of the world that has been created by this measurement act. Now, that looks very mystical. A lot of physicists hate that idea. They hate the notion that somehow human decisions or agency or consciousness is somehow involved in the nature of reality. Again, if you accept Niels Bohr's position, there isn't a single history connecting us back to the beginning of the universe, a multiplicity of alternative histories, a fuzziness as you go back in time and a fuzziness as you go into the future. This is often called Heisenberg's uncertainty or uncertainty principle. And the oddity is that what you measure helps determine the nature of reality that springs into existence. Now, a lot of people don't like that. And one way around it is to say, well, maybe all of these realities are equally real and they're parallel realities. And we have parallel worlds with parallel observers. And when you make a measurement and is the atom here, is it there? Well, maybe the world divides into many different copies.
Seems cumbersome, that one, doesn't it?
It's cumbersome. The way I somewhat pompously describe it is it's expensive on universes, but cheap on epistemology.
Oh, well, nice, yes.
What that means is you don't have to add anything to quantum mechanics. So you just take it for what it is, and you don't worry about what is an observer or what is a measurement. You just say, well, describes multiple realities, and they're all the real deal. They're all equally there in parallel. All these branches of reality are coexisting. I've flirted with that, but I don't really like it. I think it misses a trick. It misses telling us something about what is consciousness, what is an observation. I think it's an important part of trying to understand the world. But you alluded to the Carlo Rovelli's interpretation, which has to do with, I think we have this idea science is based on objective reality, so that I can describe something in the world, and you can independently observe it and check. There's a microphone in front of me. I see it, you see it, someone else can come in and see it, that we all see the same world, the same reality. And we might see it from different perspectives, but we can transform what I see to what you see. But maybe down at the atomic level, each of us has our own version of reality. That what we see is relative to what we choose to measure in the manner I've just described. And that maybe you can't simply say there is a quantum world with certain properties there, independently of what measurements we do and how we choose to measure them. And we might just have to accept that. And that's one possible point of view. There are many others. There's probably a dozen or so different attempts to interpret what seems like a mumbo-jumbo theory. Here we have a theory that works so well. It's surrounded by this technology.
Well, in a way, I've almost done your book a misservice, because I've sort of implied that it's all about this deep philosophical subject and concern with the nature of, and of course it does that.
Well, that's my real passion, but there's a lot.
But you're
in there
also
about the
interested
technology.
in the practicalities of it. You did a short list of some of the products of quantum theory before, but you're also interested in what it's going to do, the
Yes.
revolution that's coming.
We're on
Now,
the cusp
I
of that
sort of
great
want
revolution.
to talk about quantum computers, but I suspect there's a couple of words. I'm going to do a Melvin Bragg on you and say, can you briefly give us an idea of what entanglement and decoherence are? Because I think we're going to be using those words when you talk about quantum computers.
Well, entanglement's an idea goes back to the 1930s, and Einstein dreamt up this thought experiment in which he wanted to demonstrate just through thought that quantum mechanics, as I've described it, is nonsense. And this is an experiment involving not just one particle, but two that fly apart from a common center. And in quantum mechanics, they can still be linked in some way. They have common properties. And then they might fly across the room, and you'd have two experimenters. You could imagine them Alice and Bob, and they can each independently do measurements.
But this
on
is
their
linked,
particles.
but not communicating, because they can't communicate
Right.
faster than the speed of
Well,
light.
if they're far enough apart and Alice and Bob are quick off their feet, they can do measurements and change their minds at the last minute in such a way that what happens in Alice's lab couldn't possibly affect what happens in Bob's lab. And yet when they sit down after lunch and compare notes, they find that there is in fact a deep correlation between these distant measurements. And quantum mechanics predicts that there is. Einstein never liked that idea. He thought that particles would have all their properties embedded in them right from the outset, and that the fact that Alice might decide to measure this rather than that at the last minute couldn't possibly affect the outcome. The experiment wasn't done until the 1980s. Einstein was long dead, and it showed that Bohr was right and Einstein was wrong. And this property of a sort of telepathic tether between these separated particles is called entanglement. That's the word that we use. It's a particular type of quantum state, and you can produce entangled states in the lab and experiment with them. And when that work was done in the 1980s, it was primarily to settle a philosophical dispute between Einstein and Bohr. Do particles, are they born with their properties already, or are those properties brought into existence by Alice and Bob when they do their measurements? I found in favor of the latter. But it was soon realized that entanglement was more than just, a clever demonstration. It was a resource that could be exploited and indeed monetized and used as the basis for quantum information science, this quantum 2.0 that I'm talking about, and combined with another property called superposition, which I've already alluded to it. I'm talking about blended alternative realities. That this is technical term is a superposition. So if you could have many of these entangled pairs and you can blend them together in certain ways, then this opens the door to incredible technological possibilities, the most famous of which is the quantum computer, which is exponentially, in the technical sense, better than standard supercomputers.
And we need to emphasize that, because you're not talking about just being a bit better. People used to talk about Moore's law, didn't they, in which said that computing power was doubling every 18 months or something. Have we reached the limits of Moore's law for conventional computers?
Getting very close now.
But what a quantum computer is not just a better computer, it's a different animal, isn't it?
Absolutely right, because what you're doing in a conventional computer, it's true that quantum mechanics is the enabling science because it gives you things like transistors, and the conventional computer is just a sort of glorified set of gates or switches, on or off, ones and zeros. A little bit more elaborate than that, but it's a circuit where things can be switched and they're either on or off. And although quantum mechanics gives you those little switches as the materials of which they're made, there's still trillions of electrons flowing through. But with this quantum 2.0, what we have is the ability to embed the information on individual particles, so individual electrons or photons, individual states, and manipulate them at the quantum level. And so a quantum computer is actually exploiting the laws of quantum mechanics, not just to give you the technology, but to manipulate the information, process the information. And that's
And
what a quantum computer
entanglement is interesting here because it exponentially increases the number of relations.
Yes, that's right. And so a good way of demonstrating it, if you toss a coin, for example, you flip it, it comes down, either heads or tails. And to get back to our early discussion, you might not know what it is. I flipped the coin, it's between my hands, and we haven't looked to see, but we would both agree that it must be either heads or tails. And then when you look, you get some information. But in quantum mechanics, it can be in a superposition or a blending of heads and tails, maybe a little bit heads and mostly tails, or any other mixture. And so you get more than one bit of information when you inspect a quantum coin, the equivalent. If you have a row of coins, 3 coins, so you get 3 bits of information from real coins, but you have 2 to the power 3, which is 8 bits of information from quantum coins that are coupled together. And so that's where the exponential factor comes from. And so now we can imagine if you have, even 100, we don't call them coins, we call them qubits. These are the sort of like the atoms or the little quantities of information at the quantum level. If you have 100 qubits, you're in serious business. And indeed, the company Quantinuum just last week announced that they have a 94 qubits in their machine, and they're open for business, and you can send them your
well, you talk
models,
about
solved.
the exponential difference. There's a lovely statistic that a classical computer might take the lifetime of the universe to crack something called RSA, a popular encryption scheme. But a quantum computer could do it in 8 hours. I mean, that's not just a different order. That's several orders of improvement.
Yes. And I think that what has drawn attention to quantum computing is really both the promise and the threat. The threat is that it was known in the 1990s that a fully functional quantum computer could crack the codes that are used for banking transactions, credit cards, spying, email messages, and so on. Still very much in use. Still. Now, of course, the governments are hastily trying to migrate away from codes that are vulnerable to being cracked by a quantum computer. But there's nothing we can do about the stuff that's already out there in the cloud or elsewhere, stored, stolen. All of that is, you may not be able to break into it now, but if you have a quantum computer in the future, you can. And so that raises the question about all of the things we've regarded as confidential over the last 20 or 30 years could see the light of day.
Are they really practical yet? Or is quantum computing like, personal jetpacks and cold fusion is going to 20 years in the future every time you speak about it?
Yeah. Well, who do you believe? This is the trouble.
Well,
because
it brings me to the other question, because I asked about decoherence before, and we blithely say you can manipulate these things at the quantum level, but it's actually not as easy as it sounds, is it?
No. The quantum mechanics, is sort of pretty much nailed down and straightforward. But the difficulty in enabling the laws of quantum mechanics, like Schrodinger's equation, to proceed without difficulty is very, very challenging, because these states that you set up, where you embed the information in this reality soup I'm talking about, is incredibly fragile and vulnerable to any external disturbance. And so, for example, just the normal thermal agitation of molecules in the vicinity of these quantum elements is going to disrupt it and introduce errors. And there are 2 ways of dealing with that. One is that you cool down to ridiculously low temperatures to sort of try to minimize the effect of external noise. You have all sorts of screening taking place. And the other is, because inevitably errors still creep in, you have error correcting protocols, and the ability to be able to carry out practical quantum computing is going to be a mixture of these 2. I should say there are about half a dozen different ways that you can create these so-called qubits, that you can embed the information at the quantum level. We don't need to get into the technicalities.
I was going to ask,
not just
though,
one
because
particular design.
we talk about engineering at that quantum level. I can't imagine how that's done. To be fair, I have some difficulty building a mousetrap as well. But the engineering is like magic.
Yeah, I
seems to
feel
me.
exactly the same. I'm a theoretical physicist. I go into labs, I'm lost in admiration.
And they say, "Oh, we've created one space in this lattice here, and we've inserted something else into it." And
That they will do that, or
well,
trap an individual atom or ion
not your field,
in a box. And,
it's incredible.
and manipulate them at that level. It is incredible. And all of this really has occurred during my lifetime. If we'd have had this conversation when I was a student, I'd thought, well, we're never ever going to get to that stage. And yet they can do it. And that is the basis. But this problem of screening out, that's why we can't go to a store and buy a quantum computer yet, because all of the technology needed to keep it cold, keep it quiet, and correct all the errors is a work in progress. And there's hype and counter hype and major players out there, billions of dollars being poured into this. And the question is, when will we get to the point that we could crack all those codes? Or to the point that we could have much better climate models, or much better drug design? All these things are what this is the promise rather than the threat side of quantum computing. Are we talking, 2030,
Well, one
2040?
man's promise is another man's threat. You quote Xi Jinping as saying he wants a great leap forward in quantum computing. Slightly
there's
unfortunate phrase for his historical associations.
There are
But
arms race.
it's an arms race. So it's not. It's theoretical, but it's quite going to be very important because somebody will get there.
Somebody will get there, and there are claims that somebody has already got there. But the difficulty is always. Let me just explain it like this. We're used to our computers on our desktops being like general purpose computers. They can do a vast number of different tasks. But if you remember the old calculating machines or adding machines, they were not general purpose computers. They were hardwired to fulfill certain tasks like multiplication or something. You can build a quantum device that might be customized to solve a particular problem. And it might be an important problem, like something to do with drug design, but it would not be a general purpose quantum computer. And so I think what you're seeing now with these claims, we can do this by 2030 and so on, really largely refers to rather restricted devices that nevertheless could be exceedingly valuable for certain limited tasks. A general purpose quantum computer might require thousands of qubits coupled together and shielded and error corrected and so on. Is that going to happen soon? Depends who you ask. I suspect it's a little while away yet.
Well, we've talked about quantum computers. Looking forward, are there any other particular advances or devices or technologies that firstly you expect and secondly that you look forward to?
Yes, I think we've talked about the difficulty of getting quantum computers to work because they're so easily disrupted by surrounding disturbances. But if the name of the game is to measure small disturbances, if that's what you want to do, measure tiny effects, that is sensing technology, you can turn a sin into a virtue. And the upshot of that is that you can make quantum sensors that can measure anything you can think of, really, to extraordinary sensitivity. And there's a few that are favorites of mine. I've worked for most of my career in the theory of gravitation, and I like quantum gravity gradiometers. So these are quantum devices that are so sensitive to the local gravitational field that they could detect buried treasure or pipes under the ground or water or no water under the ground. They can detect the gravity change in less than a vertical centimeter because they're slightly farther from the center of the Earth if you lift them up a bit. And all of that is within the capability of quantum gravity gradiometers. So that's very exciting, but also very practical use. And these things are, out there for mineral prospecting and other functions. So that's one. The quantum clock, I've always found a fascinating concept because using quantum mechanics, you can measure intervals of time so accurately now that they wouldn't lose a second in the age of the universe.
But is there an application for that? I mean, you take it down the pub and show it to you. Look at that. Doesn't lose a second in the age of the universe.
Yes, we're not going to sit
That's
here
all
and
very
find
well. But what's the need for it? What's the application for such an accurate clock?
Well, there are a number of them. And one of these is one sort of rather down-to-earth application, which is financial services and trading, because very soon quantum computers are going to be doing the buying and selling, and all this happens in a tiny fraction of a second. And you need to log exactly who bought what when. So that's sort of a very practical thing. At the moment, you don't have to be quite that accurate, but quantum clocks are used in the GPS system. Because this helps us navigate, and you get signals from satellites, but you've got to know exactly the exact time that they come, because timing is everything, to know where you are when you're moving. And so quantum clocks in navigation it is already important, but it's going to become even more important when we migrate away from the GPS system. And just last week, the Pentagon in the US said it wants to come up with new navigation aids that don't depend on GPS, which can be jammed by anniversary. And now there are quantum accelerometers and gyroscopes and things that you can have in a submarine, for example, can't GPS anyway, that are so sensitive, combined with quantum clocks, they can measure every little twist and turn. This is the moment you turn left, this is the moment you turn right, and reconstruct the trajectory to extraordinary accuracy. So that's a very, very practical device. But the one I really like is, because there's more healthcare, it's the helmet that you will wear that measures magnetic fields with such extraordinary sensitivity, you can peer inside your head and read your thoughts, because the electrochemical activity flickering in your brain creates magnetic fields that reach outside the skull. And although they're tiny, they can be detected by these quantum magnetometers, magnetic sensors, which have such fine resolution in space and time that they could, in principle, reconstruct what you were thinking about, and could be used as brain-machine interface to operate a robot or a prosthetic device or whatever. Couple your thoughts to a future quantum computer. Maybe this is the nirvana, technological nirvana of the 21st century. I don't know, where we would literally be merging our consciousness into this sort of great cosmic quantum superconsciousness. So I'm being very mystical.
Well, Paul, you've made me feel a bit better about it all, because there are things to look forward to as well. And so thank you very much.
Oh, it's been fun. Thank you.
The book is Quantum 2.0, The Past, Present and Future of Quantum Physics by Paul Davies. It's published by Pelican at £20. Now, if you've enjoyed this interview, feel free to click on the like box and make us look good. And if you have any thoughts about it, there's a comments box as well where you can get involved in the discussion. We love to hear from you. Next time on the Books podcast, we're welcoming back an old friend, the journalist Steve Richards, whose new book is a punchy account of Tony Blair's Season in the Sun. That's one to look forward to.
That was the Books Podcast, presented by Tim Hague. Email Tim on tim@bookspodcast.com, Twitter @bookspodcast, and Facebook @bookspodcasttim.